Now let's jump into a live demonstration and the proposed design process I have for these connections. I'm going to use example 5.311 from the AISC Seismic Design Manual 4th edition. The proposed process is that still you need to use the AISC seismic provisions due to the code requirements. The first 5 steps are based on AISC 341. I will go quickly through them using some screenshots from the AISC Design Manual, for example 5.311. And then later I'm going to jump into IDEA StatiCa to show you the steps from the step number 6 to the 11, right? For the example 5.311, the braces sizes are given. In other examples, the manual shows how to design them considering AISC seismic combinations. The second step is to calculate the required strength according to F2.3. The expected strengths of the brace are shown in the example of the seismic design manual. So you can see them, the tensile strength due to seismic loading, compressive strength, and post-buckling strength. After the calculation of the expected strengths in tension and compression, the gusset geometry is iterated. In this case example, in example 11, uses elliptical clearance. I am using the first iteration to model it in IDEA StatiCa. Then the gusset plate thickness is calculated using the tensile strength of the brace connection formula. This can be used as a starting point for the model setup in IDEA StatiCa. So you can see that they are trying a 1/2 inch thick gusset plate. Finally, you need to select the beam to column connection type. So based from AISC 341, you have 3 options for SCBF connections. So you have the option A, which is a simple connection. B and C are a fully restrained connections. And for the example 11, they are using an ordinary moment frame fully restrained connection. Okay. Once you have all that information, all that initial information, now you can set up the model in IDEA StatiCa. I'm going to follow this process in IDEA StatiCa and show you how to set up the model and then also the different analyses that I am showing in these steps. Okay, so let's jump into IDEA StatiCa. As you can see here, I already set up the geometry. So we have a 12 by 96 column, 24 by 94 W section for the beam, and circular HSS for the brace, and it's a 7 by 0.5. Right, so I have already set up all these values. Okay, now let's start modeling the connection from the beam to the column. So to do that, I'm going to use a new operation, and I'm going to use a cut operation. That will be a cut M2 by M1. And I'm going to change the welds to CGP for the flanges and the web. Now I'm going to use a new operation to add notches on member M2. So I can add an opening operation, select M2 web 1, and then the shape of the opening is going to be a notch, and that will be on both sides, top and bottom of that member web. Okay, I can use the auto design option that comes with this operation, and I can select AISC Seismic Design Manual shape and geometry. Okay, now let's add the gusset operation. This is the gusset operation icon, so I click on it, and now I'm going to select member M3 to assign the gusset to that bracing element, and that gusset plate is going to be related to member M2, which is the beam, and also related to M1. So I need to select a beam element here and then be M1. Material is going to be grade 50, and as we saw, it's ½ inch thick. Now, from the Seismic Design Manual, we're going to look at the initial calculated geometry. So let's take a look on it. So you can see that for example 5.311, we have the section where they calculated the gusset plate design based on the elliptical geometry. So from this geometry, based on the choice of A equals to 41 inches, which is this distance here, then they calculate the value B, which is 35.5 inch, right? So I'm going to go back to the model and set up those dimensions. So the width is going to be 41 and the depth is going to be 35.5, right? Then we have a gap. Sorry, we have to set up the distance from the node to the starting part of this member, right? The input called gap here in the gusset operation gives you the ability to add this input here. So that's the distance from the first related member, which in this case is the the M2 member related to M2, right? To the initial part of this M3. That value is 9.5. That is also calculated from that chapter of the gusset plate design, right? Now, as an initial value, I'm going to use 5/16 for both welds for the member and the plate. If you look at the solid view, you can see the weld is set up here from the gusset to the column and to the beam and also to the member. But remember to select notch member so we have the correct weld set up. However, you can see that it's in both sides, internally and outside. So let me change it to just one side. So now we have the correct weld. Finally, we're just missing the chamfer on this gusset plate. So I can use the editor and use the chamfer operation. That will be 7 inches. And then the corner is going to be corner 2. You can also go to drawing option here and see the dimensions. Okay, I'm going to apply and then say OK. Now, one important thing is that it's better if you use the editor to add that chamfer because using that operation, it also creates this notch here on the member. This is kind of the slot. So it's important to consider that because we are reducing the area of this member at the end of the gusset plate. Okay, so it's important to have that model. All right, so as part of the second step in IDEA StatiCa, we need to run a stress strain analysis. This is with the objective of verifying that the connection is okay. I mean, you don't have any modeling error, you're not missing any connection, all right? So for that, I suggest using the gravity loads of this joint. In this case, I am not given that information, so I'm going to just use minus 100 kips on as an axial force on M3, all right? Then I'm going to hit calculate. If you see in the slides, this is the second step. Design the beam to column using gravity loads. Again, I don't have that information. I'm just using minus 100 kips on the bracing member. Analysis is finished. We can see everything is under the design limits, and then we can go to the check tab. Now here we can look at the equivalent stresses and the form shape. This is important to look at just to verify the deformation. And remember, this is your first sanity check. Okay, everything looks good. So now we go back to the design tab. The second part of that step is to run a stiffness analysis to verify the classification, if it's a simple or fully restrained. This is important when you select, for instance, a simple connection option for your SCBF, right? So that can verify that you have rotations on your beam to column connection. But in any case, it's the sanity check to run the stiffness analysis to tell you if it's a simple or a fully restrained connection, right? So to do that, I suggest copying this connection. So you're creating a new connection here, and now we can go to the connection 2, and we can change the analysis type. So we can change it to stiffness. When you change it to stiffness, you need to set up which is going to be your analyze member. So you need to tell the software what is going to what element you want to analyze the rotational stiffness, considering the connection to the other elements. All right. So you can see that M2 now is set up as analyze member. If that is, in this case, it was done automatically. If that is not the case, you can right click and set up as the analyze. The second step is to go to load effects and add a moment force on that member. This value here will activate the calculation of the rotational stiffness for this beam. Okay, so we hit calculate. Now to review the results, we can go into the check tab and look at the rotational stiffness. Here at the end of this table, we can look at the classification, and this is a fully restrained connection. You can find more information about stiffness analysis and tutorials in our website. Okay, the next step is to run a capacity design. For this type of analysis, we're going to input the expected strength forces on the bracing member, and we need to balance these forces. Okay, so let's go back to the model. I'm going to copy this connection. Now we can go to the design tab, and let's change the analysis type for this connection. So that will be capacity design. Let's go back again to the connection 3 tab. And once you select capacity design, it's asking you if it's a pre-qualified connection. In this case, this is not a pre-qualified connection. This is just an SCBF. So you can see that we have the option to run an analysis for pre-qualified connection, but this is not the case. I'm going to uncheck that option. Now this is unchecked, and now we can jump into the load effects. So before the force input, we can look at the required strength calculation in the AISC example. So let's look at it. So you can see the required strength part here in the example. And here we have some calculations for the brace above the beam and then for the brace below the beam. So the brace below the beam, it has the worst case scenario. So that's the force I'm going to use for tensile. I'm going to use 670 kips. And then for the compression force, I'm going to use 556. All right. So that will be the worst case scenario for that case. So let me go back here, and the load effect for the tension case, I'm going to rename this and put the T as at the end of that load effect name. and I'm going to put the value for the tension force. Then I'm going to copy this and use the negative value for the compression case, and I'm going to rename it to C, with a C at the end of that load effect. So one important thing is that you need to balance that force. So basically it's decomposing that force and using the column and the beam to input those forces that will help to balance this node, right? So to learn what is that force that you need to input there, I mean, we can do the math, but we can also go to connection one, that is on stress strain analysis. And for that stress strain analysis, we'll have unbalanced forces if we have loads in equilibrium active. So this will tell me what I need in the X and C value for the 670 kips axial force, right? So I'm going to use that value. And the same for the compression case. $393.15. Oops. Let me go to connection 3. Okay. The next step in this case is to set up the dissipated item, right? So basically the capacity design analysis in IDEA StatiCa, you need to tell the software which is going to be your fuse element. Remember that for this type of connections, the fuse element is the bracing member, right? So we're expecting a failure on the bracing out of the connection, okay? So to do that, you can add or click over this new dissipative item, right? So I had this before, but I'm going to delete it so you can see how is the process. So I added that item here, and I can tell the software if I need that strain hardening factor to be calculated and used. In this case, I'm not going to use it, so I'm going to uncheck that and use CPR as 1 equals to 1. Why? Because for this SCBF, we don't need the hardening factor. It's not used. It's only used the RY factor. The RY factor is going to be used for this member. Okay. So I'm going to pick by cursor so I can select the member from the main analysis. I select the bracing element and press enter. So now you can see that the item M3 is selected. And now I am ready to go. So we added the overstrength of forces on the member, and we selected the dissipative item in this model. Now I click calculate, and we are going to wait for the results. If we go back here, we are in this step where I am running the first iteration. With the expected strength forces, I'm going to see if the connection is okay. Okay, so let's go back to the model and wait for the analysis to finish. Now you can see that the analysis finished and we have a failure for local deformation and then the welds. So let's look into the check tab, right? First of all, let's look at the blades tab. And here you will see that for M3, we have this material A500 grade C, and we have an asterisk input there, okay? What does that mean? So that means that we were using a different material properties. You can see that this has an FY of 65. So instead of using the material factor, like the 0.9 here, we're using an RY factor to increase the strength of this material. So we are able to apply a huge, well, like over strength force into this member, and then we can see what is happening uh, on the connection, right? So remember that we can order by the highest stresses and plastic strain. So we can see that we have a huge plastic strain for load combination tension, the load case that has a T here, right? So in this case, what we are going to look at is the plastic strain view. In reality, for capacity design, we are interested in where the hinges form, right? So if we look at the deformed shape, we can see that here we have the highest plastic strain for the tension case, right? If I uncheck the deformed shape, you can see that the hinge is generated where we have this slot, right? So basically, we are seeing the failure in this area, and we don't really want that. We want this hinge formation out of this part of the connection, right? So um, if you have gone through the example in the AISC Design Manual, in this example, they are adding a reinforcement here because this is reducing the area of that member, so we need to kind of replace that area with a reinforcement on this HSS, right? So that is for the tension case. If we go to the compression case, in reality, we cannot see the hinge or the failure for this. So let's give it a second so you can see the compression case. There is any plastic hinge on this area. However, we need to wait until we run the buckling analysis. Okay, so for now, let's fix that, and also let's fix the welds here, because if we look at the welds for the compression case, is the one that is failing. So we have 5/16. We can increase that well to see how we can help that, right? And basically that's where the design starts. So you can look at the welds. If we will have bolts, then you will look at the bolts and then start your designing using these forces and making sure that the connection is strong enough to being able to capture those forces, right? So let's go back to the design tab and let's start iterating our design. Okay, so now let's increase the member welds here. So we change that to 3/8. Now, to be able to add a reinforcement bar here on the HSS as proposed in the AISC example, this member, you can see as the way we break out the HSS members, like with these strips, there is no way to add reinforcement. So the workaround for this case is to go to the plus icon and use the call form polygon shape, right? And input the values from the section we were used. I'm going to use 10 number of vertices. In that way, then we can work with these plates that are forming this shape, right? The thickness, though, like you remember the shape was 7 by 0.5 inches thick, right? However, that thickness is reduced because we are using a 500 grade C. So so IDEA StatiCa will reduce that to the design thickness. In this case, because this is a custom shape, that is not going to be done automatically. So make sure you input the design thickness. And then make sure you select a 500 grade C and then say OK, right? Now, you will see that here we have these plates, and now I can use the stiffening plate and place the plate there, right? So let me see. We need to change the side of the weld. Now it's there outside. And let's add a new operation. I'm going to use the stiffening plate operation. That stiffening plate operation is going to be on this M3 plate. So I'm going to use the stiffening plate. The orient is going to be the member, and this M3 web 3. It's here, it's going to be here, but now this is set up as a doubler. So I'm going to move this. Actually, is this M3 web 3? It's in this side. So we are going to use 1.25 bar thick, and we're going to give it the thickness in this side using the input H1 and H2. And the length is going to be 12 and 12 in both sides. The design requires that you add, well, not the design, but the proposed reinforcement requires that you do 12 inches in one side, 12 inches from the gusset plate plus this distance here. So I'm going to add 1.5 inch more on B2. Right? Now the weld is, well, I'm going to use 1/4. So you can see that reinforcement there. So I can copy this operation, and that'll be input in web 8. Right. So now we add that, and we increase the weld from the HSS to the gusset plate, and now we can hit calculate again. Let's see if this design iteration helps, and let's wait for the results. Now let's take a look at the results again. So let me turn off the deform shape. You can see that basically we push out the plastic hinge happening in this area. So it's just at the end of the reinforcement plate. So we can say that we are confirming the plastic hinge happening here. So that means the yielding on the brace with the tension force is happening. So if we look at the compression force, everything is okay, right? We just have some detailing checks for the welds, so we can review that under the welds tab and look at those welds that are not complying with the detailing checks, right? Now to verify that now with the compression force, the gusset plate will be buckling, right? In that with that elliptical clearance. Okay, now we can run a buckling analysis. Okay, so my recommendation here is to go back to the design tab and just keep the compression force active for that buckling analysis. Go back to the check tab and then hit calculate, and well, not hit calculating, but the drop down menu and hit buckling analysis. So that will run buckling analysis for the compression force. And then with this analysis, we can verify that the gusset plate will be buckling with that input force, which is the main objective of this of these connections, right? So if we look at the previous slides here, so the gusset is detailed such that the end rotation occurs in the connection without loss of strength. So we have different detailing checks here, sorry, detailing options, and we are using this. So for the compression force, we want that this plate buckles in this area, right? So that's what we can verify with the buckling analysis in IDEA StatiCa. So now if we look at the results, now we have a buckling factor. Remember that the buckling factor is only a factor, so uh, we need to compare this versus the recommended factors. And in this case, for that gusset plate, the recommended factor is above 4. So in this case, to be safe, we should be um, above a factor of 4. However, this is not the case here because here we are trying to see that the plate buckles with that force, okay? That the failure for the compression force is on the plate. So if we look at the deformed shape, you can see how this member is buckling um, out of plane. And then if we look at the second mold shape, is also happening uh, on the gusset plate. And all these mold shapes and hotspots are happening on the plate. Remember, these are only mold shapes, right? This is not the actual deformation, but this is just the mold shape. So here we are just verifying that the buckling is happening on the gusset plate, and we are verifying that our design is as expected. Okay, so if we go back to our process here, this is the final step to run a buckling analysis to prove that the buckling happens in the gusset plate. Okay, let's wrap up this live demonstration and presentation.